Have you ever tried describing wind without mentioning its direction? Just saying it's 10 kilometers per hour doesn't really help, does it? That's because some quantities in physics must include direction to make sense, and that's where the distinction between scalars and vectors begins. In physics, we often deal with two types of quantities: scalars, which have only magnitude, and vectors, which have both magnitude and direction. For example, distance, time, temperature, and mass, these are scalars. They don't care which way you go, just how much you have. But things like velocity, displacement, and force need direction. Saying a car is moving at 60 kilometers per hour toward the north tells a very different story than saying it's just moving at 60 kilometers per hour. So when motion extends beyond a straight line, understanding whether a quantity is a scalar or a vector becomes crucial. Let's understand scalars a little more. These are quantities that are fully defined by just a number and a unit, no direction involved. Take this example: the length of a rectangle is 1 meter and its breadth is half a meter. If you add the lengths of all four sides, the perimeter comes out to 3 meters. Each of these sides is a scalar, and so is the perimeter. Now let's look at temperature. Suppose the maximum temperature in a day is 35.6 degrees Celsius and the minimum is 24.2 degrees. The difference, 11.4 degrees, is also a scalar. Let's take density as an example. The formula for density is ρ equals mass divided by volume, or ρ equals m over v. Here, we are given the mass, m, as 2.7 kilograms and the volume, v, as 10 to the power of minus 3 cubic meters. Now, substituting the values into the formula, ρ equals 2.7 kilograms divided by 10 to the minus 3 cubic meters. Solving this, we get ρ equals 2.7 times 10 to the power of 3 kilograms per cubic meter. This shows how scalar quantities like mass and volume combine through division to give us density with a new derived unit. Now let's bring in the heavyweights, vectors. These quantities carry both magnitude and direction and are represented using arrows in diagrams or bold letters in equations. So, what makes vectors special? Well, their direction can dramatically change what they represent. A force of 10 newtons toward the left is not the same as 10 newtons toward the right. Displacement is another classic vector. It's not just how far you've moved, but also where you've moved. We usually represent vectors using symbols like bold V for velocity or R with an arrow on top for position. The magnitude, or absolute value, is often denoted with vertical bars. For example, magnitude of V is written as vertical bar V vertical bar. Vectors follow geometric rules. They obey the triangle and parallelogram laws of addition. And you'll soon see why that matters when analyzing motion in 2 or 3 dimensions. Imagine standing at a park entrance. We'll call that point O. You walk straight to a bench. That's point P. The line from O to P is called the position vector, and it tells us where you are relative to the starting point. If later you walk to a new location, say point P prime, the new position is represented by a second vector. The change in your location, that is, the vector from point P to point P prime, is called the displacement vector. Now here's the interesting part. It doesn't matter whether you walked in a straight line or zigzagged through flowers. The displacement vector is simply the shortest path from your starting point to the final point. As you'll see in the diagram, 3 different curved paths from point P to Q all have the same displacement vector, a straight line from P to Q. So remember, displacement depends only on the initial and final positions, not the path in between. Let's talk about what makes two vectors equal. It's not about where they are on the paper, it's about how long they are and which direction they point in. If two vectors have the same magnitude and direction, they're equal, even if they start from different points. These are called free vectors because we can shift them parallel to themselves without changing their identity. Imagine two arrows of the same length, both pointing northeast. If we slide one next to the other, their tips and tails will match perfectly. They're equal vectors. Now suppose two arrows have the same length but point in slightly different directions. Even though their magnitudes match, they're not equal because their directions differ. As the diagram shows, vector A and B align perfectly, they're equal. But a prime and B prime, though same in length, are not equal because they point differently. Let's apply what we've learned with a quick classification example. I give you 4 quantities, you tell me whether they're scalars or vectors. First, velocity of 20 meters per second toward the east. This has both magnitude and direction, it's a vector. Second, mass of 5 kilograms. Just a number, no direction, it's a scalar. Third, force of 10 newtons acting at 30 degrees. Magnitude and direction? Definitely a vector. Fourth, temperature of 300 Kelvin, no direction here. It's a scalar. Let's bring it into real life. The wind blowing northeast at 10 kilometers per hour is a vector. But your body weight of 70 kilograms, that's a scalar. Pretty straightforward, right? So let's quickly summarize what we've explored. Scalars are quantities that need only magnitude like mass, time, or energy. They follow simple arithmetic. Vectors, on the other hand, are quantities that require both magnitude and direction. They follow special geometric laws and are key to understanding real-world motion and force systems. Displacement is a great example. It only cares where you started and where you ended, not how creatively you got there. And when two vectors have the same size and point the same way, they're equal, even if they're not drawn in the same spot. Mastering scalars and vectors sets the stage for everything that comes next in physics, from projectile motion to circular dynamics. I hope this session gave you a clear and confident understanding of this foundational concept. See you in the next class, where we'll take the next step into multiplying vectors by real numbers.